Okay, I've cleaned up this page a little bit so that the annotation is easy to read. It's time to start the lecture, so welcome to week 3. And so before we can actually start with bases and dimension and linear transformations, I promised you to go over this last theorem that we ended up with last week. And I've actually after the lecture, I realized that I'm going to be using this theorem a couple of times this week. So I'm just going to give this a name. This is going to be the uniqueness theorem, so that you know which one I'm referring to. It might have a number in the book. I'm not certain at this point. But what does this theorem say? Well, it says that suppose we have a family of vectors, and we denote this by S, and this family is linearly independent. And we've defined what linearly independent means before. Now, the span of S is also a subspace in V. And we know that S, by definition, span S. That's the whole point of defining span S. Well, and now what we're claiming here is that if S is linearly independent, or we can say that S is linearly independent, if and only if every vector in span S has a unique representation as a linear combination of the vectors in S. The fact that there is some linear combination isn't hard to see, because if it is in span S, then it just differently said that span S is the set of all linear combinations. So if it is in there, some vector, then it is a linear combination. The really important part of this theorem is that there's only one unique representation as a linear combination. Okay, and then the proof. How do we see this? Well, if we first suppose for the forward direction that v1 to vk is independent, and we assume the opposite of what we're trying to show. That is to say that we're assuming the opposite and then showing that this is a contradiction, and then we know that the direction is proven. So we assume that v1 to vk is independent, but for some vector v in the span, there are two ways to write this in terms of the v1 to vk as a combination. So this may be the first one, and this is the second one. Well, what does this mean? Well, if we subtract these because they're equal, we get 0. So that's what we do in the next step. We subtract these two combinations, but because they're both equal to v, this gives us 0. So we have the first combination minus the second one. But because the operations in a vector space are associative, we can reorder them. And we can also group together all the terms with the vi, all the terms with the v2, and so on. So what we get in the end is an equation that is highlighted here in green. But now observe that this is exactly the equation that you consider to check whether the v's are independent or not. And if they're independent, we know that this linear combination is only equal to 0 for the trivial coefficients, for the trivial combination. So then by assumption, if v1 to vk is independent, this means that each term, each coefficient, alpha 1 minus beta 1, alpha 2 minus beta 2, and so on, will be 0. But this just means that the coefficients are the same. So we can conclude that these combinations are actually the same. Now, for the converse, I want to show that that if every vector in span S has a unique representation, then S is linearly independent. And for this, we can use the it is equivalent to show the contrapositive. This means if you have two statements, A and B, then A implies B is the same as not B implies not A. So what I want to show is that not independent implies not a unique representation. But what does it mean? So not independent means, of course, dependent. So if you assume that they're dependent v1 to vk, then there's the reduced theorem, which says that for some index j, there is a vector v sub j in the span, or in the family S, that we can remove it, and it's still in the span, and then the span still is unchanged. So now, in other words, if we pick this vj, then two things. We know that it's in the span S because vj itself is in the span S. So we can write the first combination, which is just which is very simple because it just contains vj and all other terms are 0. But because of the reduced theorem from late last week, we also know that if we remove vj, we don't lose anything in the span, including vj. So for some linear combination that doesn't include vj, we can still represent vj. But this means we have found a vector, just a single one, that has two combinations in the span. And this is enough to show that the opposite of the second statement is true. So this concludes the other direction. Any questions? The intuition, which you didn't see properly last time because my screen froze, is just to say that we saw before that a linear combination of vectors can be thought of as a concatenation of these vectors to a path. And it's the trivial combination is just a point, and the combination is equal to 0 if the concatenation goes back to 0. So it starts at 0 and it goes back to 0. Now, if there are two combinations for the same vector, say this vector, this point, this yellow point here, if there are two combinations, then what we can do is we can go the green one forward and the red one backwards, which it results in a loop. So this means that if I have available all the green arrows and all the red arrows, then it's equivalent, and then you can see that there are two paths which are not the same. They're distinct linear combinations. If and only if there's a loop. If these were the same, then this loop would not be. This loop would be trivial, because if you go one path and you go back the other, then that's the same as not going at all. So then they cancel. Yes, this notation here, I think I said this last time, but let me repeat this. This always means, so a hat always means you remove the object. This item removed. Okay, I don't see any hands up. Any questions? Yeah, and the contrapositive, what we did was we used this vector directly. So we used this vector, which was a combination for itself, and then also some other combination not involving the vector itself. Andrew, you have a question.
Yeah, I just needed a bit more clarification about the hat notation. So if we mark a vector with a hat, does that mean it's already been removed from the set, or is it still in the set, but we're gonna remove it later?
Well, it means in this instance, it is removed. It doesn't appear. So let me just write this down here. So if I have, say, vectors v1, v2, vj removed, vk, this is the same thing as v1, v2, vj minus 1, vj doesn't appear, vj plus 1, vk.
Oh, okay. So vj is no longer an element of the set.
Yes.
Okay, thank you.
Okay, let's go with these true or false questions. I'll give you 2 minutes to look at these. Don't go over all of them, maybe, if it's too much. If these are too many, but just look at some of them and just pick one, your favorite one, and then answer this later. And then hopefully to every question, some student has an answer. All right, pick your favorite item in the list and tell me yes or no. Oliver.
Well, I picked one and the second last one, but I guess I can start with the first one. And I believe the first one is true because we can use an example. For example, um, uh, let's say we can use the third R3 and R2, and R2 is a subspace of R3, and R2 is also independent.
Well, it's always a good idea if you want to prove something to not use an example because it doesn't show the general case. And then also you mentioned subspaces and not families of vectors. So we're looking for families here. But let me just make a quick comment on how I would see this. Well, if v1 to vk is inside v1 to vk plus l, so we added l vectors to the end, then and alpha v1 plus alpha vk has non-trivial solution. Well, if we just add the other vk's, the vk plus 1 to vk plus l, so does alpha 1 v1 plus alpha k vk plus alpha k plus 1. That's getting, let me just say, and so on until alpha k plus l. Vk plus l. So meaning if you just forget about the vectors added to R to get S, and you have a non-trivial solution, then it's still a non-trivial solution if you include the other vectors with 0 coefficients. Okay, Sijin, you said in the chat the last one is false. Can you explain that?
I think because we can only have two independent polynomials in a P2.
It would be 3.
Oh no,
but,
3,
but
because
yes.
we also have the constant one. Yeah.
Yes, exactly. Yeah. Yeah, let me not write anything about this. But let me just leave it at this because I want to move on soon. But that's completely correct. And actually later today or tomorrow, we're going to have more machinery to argue about this, and then it'll be easier. So if this is confusing now, just wait 24 hours and you'll know more. Okay, more answers. Andrew said 3 might be false. Okay, what is this?
Yeah, I said 3 is false because if you include the zero vector and the non-zero vector in the set, like one is a multiple of the other, and but the other namely the non-zero vector is a the zero vector is a multiple of the non-zero vector, but you can't say otherwise.
Yeah. So this is dependent. They're completely correct. This is dependent, but V is not a multiple of 0. Okay. Any more? What about the second one? It's basically the same answer. Yes, exactly. Someone just said 0 vector. I like the brevity of this answer. So let me just write here that this is a family with a single vector, but it's dependent because any combination of this actually is 0. So there's nothing else to show. What about the fourth one? Actually, let me think about this myself for a second. No, that the second one is yeah, it's false. Yeah, that's what you said. I'm getting confused with my own logic, but this is false. And the counterexample, let me just write this down here. Counterexample, well, let me pick a really weird one. Well, 100 with itself is dependent. But if you remove one of them, then this is a subfamily. I mean, I didn't define this, but it is just a family that is contained in the other family. Yeah, I mean, in Gen Z had the same idea, only that I went to seem shorter the answer. And Andrew has a good point. I guess families are not sets, but it doesn't matter. You can make this argument work without having duplicates. That's not the point here, but it is a good point that maybe we don't want to have duplicates, but still we could have 1 1 0 1 0 0 0 1 0. This would be dependent, but if you remove one of them, it would be independent. So that works. What about the second last one? What about this one? Yeah, this is definitely true. And we've seen this. So we've seen this in the lecture before. There was a theorem about this, in which case spans are equal. Namely, if R is contained in the span of S and S is contained in the span of R, then they're equal. So I'm not going to say anything else about this. And then one more, family. Yes, this is true, I believe. Do you all agree? Yeah, because I think actually this is kind of the same statement as this one. So maybe compare these ones. I think they are actually equivalent. I might just repeat it myself there. Yeah, James just said it's like the first one. Okay, any questions? I know this was like a very rapid walk through these true or false, but maybe if you have more questions, you can think about these for a bit more, and otherwise ask me in the office hours. Okay, then with 20 minutes delay, we'll start with today's content. And I think this is going to be a very interesting lecture, like an interesting week, because this content is getting more abstract. It's getting also more beautiful. There's lots of things that fall into place, as you'll see in the end. And I think that's very neat. Just before we start, a quick warning. So I kind of got overly excited about this topic, I guess, and I kept adding more content to this week. And maybe, just maybe, there's a little bit too much in this week now that we won't be able to cover all of this. But don't worry, it's better to have too much content than too little. And if you don't get through all of this, just view this as a source of learning material or study material. So I'll still go slow, slow enough for everyone to hopefully follow. All right, so before last week, we have seen two things: independence and spans. And now the first definition combines these two. So now what we want to do is we want to say, well, can we have both at the same time? So this means now we have a family of vectors, and this is called B for obvious reasons. And we call this a basis of V if it is both independent and it spans the vector space. So we just clash together two definitions we've had before. Before I tell you why this is important or why this is useful, which will actually take all of this week, let me give examples so that you have something to keep in mind when we go through the more abstract things. So the first one is, as always, E1 to En. Remember, these are just the standard vectors. So Ej is just a vector with a 1 at the jth position. So the jth entry is 1, everything else 0. And if you have n of these, then this is the basis of Rn. And we've seen before that this is independent, and we've seen before that this spans Rn. And actually, if we go back in week 2 to the very top, I think, yes. So if you look at this at the first page on the bottom of last week, this is exactly the explanation why it spans R3, and this same technique works for Rn as well. So last week, what we've seen is we've had the set with 3 vectors. We had these two. We had 1, 1, minus 1, 1, and 2, 0. Remember that this looked something like this. We had a vector like this, and like this. And if we remove the red one, which is 2, 0, this was part of the reduced theorem, then we'll actually end up with 2 vectors which still span R2, but which are also independent. So they span R2 and they are independent. So by the definition, this is a basis. So how about P2 of R? Well, certainly, what we've seen before is that the set, the family containing the monomials 1x and x squared is a basis. But this is just like having the E1 to En basis of Rn. So I also want to know, maybe is there a basis which is somewhat more non-trivial, which doesn't contain just monomials? And well, another basis, let me call this B prime. I can have 1 plus x. Let me go back in last week's lecture, last week's slides. We had this one example right here. I mean, it was for P3, but the same idea was that we had two different sets. We had this one with the monomials and then something else, and they both spanned P3. So now, similar to this, which was on page 4 for your reference, I can build 1 plus x. Maybe I'll add x plus x squared and 1 minus x squared. I think this should be a basis. Does anyone disagree? If you try to set this to 0, then I mean we can cancel these ones here if we subtract this from this. So if the coefficients of these two are opposite sign, then the one will be gone. But we'll have an x minus x squared and an x plus x squared. So no, they are independent. Believing is good, but you should always check for yourself. All right, yeah, and please do check these things that I just say. Right. Sorry. Yeah. Sam is correct. Sam is right. This is not true. So what if you have 1 plus x squared? Does that work? I mean, this is basically a discussion. So, if you now subtract, yeah, I think this should work. Okay, this is a basis. So we've solved this second question here. Okay, let's have a discussion about this at the bottom. Did I miss any questions? If you have questions, just raise your hand. Then I'll go into more detail. Okay, so I'll give you 2.5 minutes to discuss this. Well, we've seen before that that because these span R2, there is a combination of these that gives us 5,3, the vector 5,3. And I want you to find all combinations that are equal to 5,3. In the chat, someone wrote, what did they write? So Idris said something about factoring out an x. Well, that is true, but remember that multiplication of monomials isn't part of the vector space addition. So we can't use that operation. Okay, I see that some of you are chatting in the chat. Can someone maybe say for everyone out loud what do you think?
4 times the first vector minus the second vector, and that should be the only combination because the two vectors are linearly independent.
Yes, correct. I don't think you raised your hand. Someone else raised your hand, but so please raise your hand first before you unmute yourself. But the answer is correct. So let me just say, let me start from the beginning and explain that a little bit more. So we want to find that 5, 3 is equal to some multiple of 1, 1 plus some multiple of minus 1, 1. And this is just alpha minus beta in the first component and alpha plus beta in the second component. Now this gives us a system of equations. Namely, we see that alpha minus beta and alpha plus beta have to be equal to 5 and 3. And I mean, the system can be written as 1 minus 1, 1, 1, alpha beta 5, 3. Now, all this is a little bit of an overkill for this simple question, because you can just look at it and try out different alphas and betas. But I still wanted to mention this because the way of writing down, of setting up the system of equations will work in any general case. And even if it gets more abstract, then we can use this to find solutions and make arguments and argue about this. Well, now we can see we could potentially reduce this to the row echelon, but let me just and the row echelon form would be 1, 1, 4 minus 1. So now this means that indeed alpha has to be 4 and beta minus 1. And we can actually check that 4 times 1, 1 plus minus 1 minus 1, 1 is equal to 5, 3. Now, the other question here is, well, is this the only combination that we have? And there's now different ways to answer this. And I believe that in the chat, there was the right answer somewhere in there. It was the uniqueness theorem from just now that we reviewed at the beginning of the lecture. Let me try to shrink this down. And now we can say that I want to call this S. Because this is a basis, by definition, we know that S is independent. Well, and then the by the uniqueness theorem, every linear combination in span S, which is equal to R2 in our case, is unique. So that there can't be any other combination that's equal to this combination. Another way of seeing this in this case would also be to say that the system that we set up to find alpha and beta doesn't have any other solutions. It has a unique solution. So that would also be valid. Any questions? Okay. I hope we get at least 2 more pages done today. Well, the next theorem is exactly addressing what we just observed in the discussion. And well, it says that if we have a basis of a vector space, then, and this is kind of the uniqueness, a uniqueness theorem for bases and not just independent sets, because the only difference between an independent set and a basis is that the basis also spans the whole space. So if we go back to the uniqueness theorem, then we didn't assume that the span is all of V, which is fine because we just said something about combinations in the span and not every single vector. So now this is almost the same as the uniqueness theorem, and from now on we should call this the uniqueness theorem. But it says exactly that if we have a vector space with a basis, then every vector in this vector space has a unique representation as linear combination in this basis. And vice versa, if we have a set where every vector in the space can be expressed uniquely as a linear combination, then this is a basis. The proof is leaning heavily on the previous work that we did. And so if you say that B is a basis of V, then I'm just gonna do this the brief way. I'm gonna just write equivalences in this proof. This is usually not the best form of proving something. It's better to go one way and then the other way back separately. But let me just break this rule here. So if it's a basis, this is equivalent by definition. So we have, by addition, this means that B spans V and B is independent. Okay, and then because B spans V, this means for every V, there is a combination and I often just use the wording that this can be represented in the spaces, by which I just mean there's some combination equal to this vector. But because we also have independence of the family B, this is by a theorem, every combination is unique. And this is all we need to show. So for the other way around, if you want to go backwards, and we say, well, if for every vector there's any combination, then we first focus on the fact that there is a combination. So this means there's no vector outside the span, meaning that B spans V. And then because we also had an if and only if in the previous theorem, we can say that because this is unique, B is independent. And then these together imply that it's a basis. Okay, let me squeeze in one more theorem at least for today. So after this, yeah, I think we can get through with one more theorem, unless there are questions. They take priority. Okay, so I labeled this extend and reduce part 2, because similarly, I mean, last week we did a lot of heavy lifting of in terms of propositions and theorems, and today we're gonna just extend them a little bit. We're gonna make them a little bit stronger in the context of bases and dimensions. So what does this say? Well, it says if we have a vector space which is spanned by a finite set, and I'm gonna make a comment about this later. So for now, we can kind of disregard this. So let B just be a vector space, and what I'm going to say is that every linear independent family S can be enlarged to a basis B containing S. So this means we may add vectors to this family S to make it into a basis. And the second point is, and this is in the book Theorem 166. I don't know why the second part isn't in there, because it's just this, I think it should be part of this theorem. It should be also included. The other point that we can make is that every family that spans V can be reduced to a basis contained in S, right? So the idea is that if we have a family S which is too big, then we can carve out, we can remove the unnecessary stuff, and we can carve out some B which is a basis. On the other hand, and this would relate to part 2. The picture to the first statement is that if you have something which isn't yet big enough, so you have a family which is independent but doesn't span the space, you need more vectors because the span is too small. Then you can enlarge this and you get a basis. Okay, so the proof will not take very long because we did all the heavy lifting last week. So by the let me just do this case by case. So if we have an independent set in V which doesn't span V, then by the extend theorem, let me just show you what I mean. Right, so this is the extend theorem. It says that if it doesn't span the whole space, then Zoom disappeared. If it doesn't span the whole space, then there's some vector in V that is outside the span, and well, that's the first assertion, that this vector exists. And the second one is if we add this vector, it's still independent. So in this case that we're in, there is some, this is by the first assertion, there's some V in V, not in span S. And if we add V to S, maybe let me say S prime is equal to S union this V. S prime remains independent. So if we do this once, we have two cases. Either now it spans V because we've added something, or it doesn't. If it doesn't, we just repeat this process. So repeat this process until span S prime prime, however many primes we need. So until S prime prime, I don't know, we have to iterate over this a few times until the span is equal to V. And the only this process only terminates if we can't find a V anymore to add. But this is fine, because if there's no such V anymore, then we're done with our iteration. Then the span is already V. And we are guaranteed that S prime prime prime, or however many primes you want, we need there, is still independent. That's a very important assertion of the extend theorem. So we're going to cycle through this multiple times, and every time you do this, it's still independent. This will never change. But if you do this often enough and we get that it also spans V, then we have both. We have that it spans and it's independent, and this means we have a basis. Any questions about this? Oh, it seems like Jose appreciates this theorem. It's nice to hear. So let's do the second one. It's kind of the same idea, just upside down. Now we have too many vectors and we need to cut down the things we don't need. So the second one is that now we indicate that the family spans V, but it might not be independent. Well, if it is independent, then there's nothing to do and it is a basis. By the reduced theorem, there's some Vj in an S. So for some index, some vector Vj in there, that can be removed, such that S prime, which is S without Vj, I don't know, did I have better notation before? Let me check what I wrote earlier. No, I think this notation is fine. So now we removed one. And the span of S prime is still the span of S, which is V, which is unchanged. Maybe I should be more specific here, because if we do something, if you apply a theorem, I want to encourage you to very thoroughly check the assumptions that are being made. So what I should say here, I want to include that the reduced theorem wants the set that we start with to be dependent. So if S is independent, we have a basis. That's already done. Then we're done with the proof. If S is dependent, then by the reduced theorem, then it actually tells us something, because let me go back to the reduced theorem. So the reduced theorem says that if we have a linearly dependent family, so it doesn't work with any family, it has to be dependent. then we can find for some index a Vj such that the Vj can be removed. That's the second part here. Span doesn't change. Now, similar idea to before, repeat this. Repeat this process until S prime, 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 and so on is no longer dependent. And notice again that this can be repeated if it is dependent. As soon as it is independent, this theorem doesn't work anymore. It doesn't apply anymore, but then we don't want it anymore. Then we already done. So now this implies, now we have an independent set that still spans V, because the span wasn't all these iterations of removing one element and again didn't change the fact that the span is the span. If you look at in week 2, the span is never unchanged. That's very important. And this means that we have a basis. Okay, so the reason, just a quick remark, the reason that I want a finitely spanned set is because this iteration of doing it again and again and again only terminates if I eventually have enough vectors in the span to span V. So this would be a problem if we work with all polynomials. Then you can always add another power. You can always add x to the n plus 1, and so on, and you will never be done. So if we need infinitely many monomials to span something, then I don't want to talk about this in this course. There's something to be done, and there's some course about this, but if we get into this territory, which we'll later be calling infinite dimensional, then I don't really care about this in this course. So that's just a technical issue, that there's this assumption has to be made. All right, and so this is kind of the intuition behind this, that you can tell that a basis is kind of a very narrow line in between too big of a family and too small. If it was too big, it would have redundancies and it would not be independent. If it's too small, it doesn't span the space. So this kind of a sweet spot that you have to dial in order to get a basis. And this is the remark too. So intuitively, and these pictures here, I think help. If you dial a family of vectors up and down, then there's one sweet spot, and this is exactly the idea of a basis. And also, if you start with any set that is independent or that spans, the cool thing is, by this theorem, we get a corollary that every vector space, every finitely spanned vector space has a basis. Yes, and this is the end. Someone already asked if they can leave. Yes, so this is it. I'll stop here. We'll start with the discussion tomorrow. But I just wanted to finish this idea because these two constructions tell us that that every vector space, which is finite in some sense, has a basis, and that this is quite useful. We're going to use this in the future of these this lecture this week. Any questions? You're all free to go now. I'll not add anything at this point.
Hi, Professor. So, just for clarification, is the basis for R0 just the empty set?
The basis for R0. Yeah, I think there's some convention to be made so that this works out.
Yeah, because I was thinking that since the set containing only the zero vector should not be a basis for the zero vector, right?
Yes. So yeah, and later, as a spoiler, we're going to talk about dimension tomorrow, which will be the number of elements in the basis. Then this should have dimension 0.
Oh, okay.
So along by this, I don't remember what the textbook said, but along by this, it should be clear that we want the basis for this to be empty.
Okay, thank you.
Sure. Mallory.
Hi, I just had a quick question just about number 2 from the true or false. It was false, and there's a counterexample of a set just containing the 0 vector. I'm just curious if there are any other examples, or if that's like a unique case. Like I can't think of any, but
no, that's the only counterexample.
okay, perfect. That's great. Perfect. Thank you so much.
Okay, you're welcome. Sijin?
Oh wait, never mind.
Can I ask a question also about the true or false?
Yes, absolutely.
Last two one. I'm still a little bit confused about the theorem that you said we learned it before.
Oh yes. Let me make this more precise then. So where did we have it? I think it was this. Do we not have this? No, wait, where was it? I'm getting lost in my own notes. Yes, so this discussion here. So if you try to forget about all these annotations, then what this said was that the vector space P3R. And we know that this is spanned by the monomials 1x, x squared, and x to the 3.
Yeah.
But what we've shown in this discussion here is that the span of these vectors, of this family of vectors, is also equal to P3R. Now, this means that the span of, let me highlight this. So this means we have two families, this one and this one. The span of them is both P3R, which I wrote here. But yet the families have different elements. For example, x minus 2x squared is an element in the span of this, but not in the set, not in the family of this.
So the family is different, but they have the same basis, actually.
Well, a basis doesn't. A family doesn't have a basis. Vector spaces have a basis.
Yeah.
But they generate. They span the same vector space.
I guess I kind of get it. Yeah.
Another example, maybe that's more helpful. Here, that's even better. So this was page 4, and now we're on page 5 of last week. Here you see that R2 is spanned by these two vectors, E1 and E2.
Yeah.
And these three vectors, but even if you forget the last one, so if you strike this out,
yeah,
these two still span R2. And here you can see why. If you have any point in here, say this one, then you just have to go to the right a little bit with this vector and up to this with this vector. Yeah. So it spans R2. Likewise, if this point was here, maybe not exactly there, but maybe it was here, then we can use this vector to go up to the right, like to go
Yeah, so we can still get that,
northeast,
that point.
and then we use this one to go northwest, and then we get here.
Yeah.
So it is certainly possible that two families are not equal, but they span the same space.
Oh, okay. Yeah, that makes sense. Yeah, thank you so
Okay.
much.
Sure. Rosalind. I can't hear anything.
Sorry. I think someone raised their hand before me.
Oh, is that true? Okay, then please, what's your name? John Wan? Is that how you pronounce it?
Hi. I was wondering about the true or false, a family V of a single vector is always independent. Why is the zero vector a counterexample? Because
because the vector, any family with containing a zero vector, so a linear combination with vectors, let me call this maybe R, in R is just a multiple of the zero vector. And if there was not a vector in there, say V, then this is alpha 0 plus beta V. Well, but now you see that as long as, no, in any event, this term will always be 0.
right.
No matter what alpha is. So now if you try to find 0 is equal to alpha times v1, which is 0 vector, plus beta v, then this has non-trivial solution. Actually, let me now remove this beta because we actually only want to talk about this. So it has a non-trivial solution. Alpha equals anything. Anything not 0. And the combination is always 0. And it's a bit of an extreme case. But a non-trivial solution just means that not all coefficients are 0. There is just one coefficient here that's non-zero, so it is non-trivial combination, which is 0, and that means it is dependent.
Wait a second. Wait, so you used like if you multiply the zero vector by any scalar, you'll get the zero vector itself, but then isn't the alpha times zero vector, that's not in the set, right?
No, it's not. So if you have a family of vectors and you multiply this by any number, then you're not guaranteed to be back in the set, but you're always guaranteed to be back in the span. So this is I mean, if you compare this one word by word with the definition of linear independence and dependence, then I think it will be clear if you keep in mind that any scalar times the 0 vector is still 0, and here I mean the vector. So this is always 0 for any alpha. It is to say that if you have a vector which is non-zero, then you can scale this. This is alpha times w. This is alpha. This is w.
Oh, I see. Okay.
But if you have the 0 vector, which is literally just a point, which is just not going anywhere.
Yeah.
If this is 0, and then you have 5 times 0, well, it's still the point.
Right. Okay, so in other words, it's like what is it? Like 5 times 0 is, or 0 is dependent of 5 times 0. which is dependent of 6 times 0?
I wouldn't formulate as that. I would say that I mean, what we want is non-trivial combination, and any non-trivial number here will give us a non-trivial combination. The only confusing thing might be that we only have one vector in here.
Right.
Usually we have a family with more than one vector.
Okay.
And because we have a non-trivial solution, something non-zero, such that this combination, which usually has more terms in here,